All right, we are back. Happy Wednesday, July 8th here. We are moving on to chapter 20. This is part one for chapter 20. We are grading test one. Key is posted on Learning Suite. If you have any regrading issues, you probably shouldn't though. It's multiple choice. So check the key carefully and double check, especially the problems you missed. Remember, the final is cumulative, so you'll get a second chance at some of those problems again on the final there. Also, we have quiz 4 coming up, which is due tomorrow. You'll have a session with the TAs, recitation to help you out with that. But again, it's make sure you get the PDF off of Learning Suite, do it, and then upload that by Thursday night. Homework 5 is due Friday. We're not finishing chapter 20 today. Get a little break there, and then your homework's due on Friday there. But we'll also start chapter 21 on Friday. So we'll finish up 20 and then start 21 also there. So let's look up here on the course, the chapter outline, and see what chapter 20 entails here. Carbonyls, ketones, aldehydes, esters, a little bit on amides and acylchlorides, all kind of be thrown together here. The key unifying idea is the idea of adding nucleophiles to these. So we'll have aldehydes and ketones here undergoing nucleophilic addition. We've already talked about how this works, right? The nucleophile with a pair of electrons coming in, pushing the electrons up to oxygen. And when you work up the reaction, quench with water, you get an alcohol product. Now that's with aldehydes and ketones. But with carboxylic acid derivatives, where you have an X group here on the side of the carbonyl, when the nucleophile adds, you get the same tetrahedral intermediate. But look, the X group is a what? A leaving group then. Under those strong conditions, basic conditions, you can bring the electrons back down and regenerate the carbonyl. So you get back the carbonyl stability in that case, and you get a new nucleophile on the acyl group there. Now, if you have excess hydride or carbon nucleophile reagent, the Grignard reagent, then you can go on and add a second equivalent of nucleophile here, okay? So if you keep the paradigm here straight for the reactions, this should be okay. Now I have to warn you, this chapter is very reaction heavy. So we've got to keep track of reactivity. What substrates, what reagents give what products, okay? The mechanisms are relatively simple. They're kind of repetitive, the same kind of thing following the paradigms here. But you need to keep track of the reagents and the reactivity there carefully. This is an idea, if we're using hydride reagents, it's an idea of reduction. So reduction means adding hydrogen or removing oxygen. Oxidation, just the opposite, means adding oxygen or removing hydrogen, okay? So if we reduce a aldehyde with a hydride, we go to a primary alcohol. Reduce a ketone, we go to a secondary alcohol. The derivatives can either go to an aldehyde or an alcohol, depending on what the reagents and the conditions are. So reduction, these are the new reactions here in chapter 20. We'll use two different reagents, sodium borohydride right here, and also lithium aluminum hydride, LAH. It has its own acronym there. These are similar to hydrogenation, you can say, of alkenes. We're hydrogenating, you could say, a carbonyl now. Adding hydride, though, it's a polar process. We'll talk a little bit about some chiral reagents, the CBS catalyst of Cori. You've actually seen that before. I've shown you the synthesis of Tamiflu. We'll also do Mother Nature's hydride reducing agent, which is NADH. You've probably heard of that cofactor in biochemistry or molecular biology or even biology class. They've gone over metabolism. NADH is a reducing agent. NAD plus is the oxidizing agent. So we're covering this topic mainly because it fits into metabolism later on and biochemistry. So carboxylic acids and their derivatives with lithium aluminum hydride all go to primary alcohols. Then we have some selective reagents. Lithium tri-TB-toxy aluminum hydride with acid chlorides go to aldehydes, and diabol, diisobutyl aluminum hydride with esters, stops at aldehydes. So those two reagents aren't as aggressive as LAH. LAH, all the derivatives go all the way to a primary alcohol. There's a little twist here. Amides with LAH give an amine, not an alcohol. And that comes out of the mechanism. Once you're comfortable with the mechanism, that won't be too bad. Oxidation. We had this topic in chapter 12, actually, in 351. And this is oxidizing primary alcohols to aldehydes, secondary alcohols to ketones, aldehydes to carboxylic acids. We know how to go all the way with chromic acid here. The only new reagent is silver oxide, the Tollens test. That will oxidize an aldehyde to a carboxylic acid. And it will not react with alcohols. That's the difference there. Now, the other main new topic here, besides the hydride reagents, I told you this was reaction heavy, right? So yeah, we got 2 pages of topics here. And the keys here is the organometallics. Now, don't be afraid of these. They're just like other nucleophiles, okay? But they're carbon nucleophiles. We have the lithium organometallics, the organolithiums here. We have the acetylene anions. Actually, we saw those before in 351. That's just the deprotonated terminal acetylene to give the sp2 hybridized carbon nucleophile. We've talked about that, but now we're using all sorts of carbon nucleophiles. The most convenient one, the most useful ones, the Grignard reagents. These are the alkyl magnesium halides. Again, they're carbanionic. The R group here will be the nucleophile. Okay, and we have a other one down here. Yeah, the cuprates. Organocuprate reagents. They're also they're specific for enones, unsaturated carbonyls, and you'll see how they're different. They do conjugate additions, we say, and put an alkyl group at the beta position there. But the Grignards are the most versatile ones here. If you add a Grignard reagent to formaldehyde, for example, you get a primary alcohol. With aldehydes, they go to secondary alcohols. With ketones here, Grignards go to tertiary alcohols. Esters and acid chlorides add twice to give tertiary alcohols. And then we add in some other electrophilic reagents, right? We add in carbon dioxide, which reacts here to give carboxylic acids. We use epoxides. We've had epoxides openings with nucleophiles before. Those give alcohols. And enones give alcohols via 1,2 additions. So we'll see the alkene ketones. That's what an enone is. It's a contraction of those 2 terms. We'll see them both with Grignard reagents and down here with the organocuprates. Protecting groups, sometimes we need to mask the reactivity of alcohols within a substrate. So within the R group, there's a ketone or aldehyde or some other electrophilic group we want to react with, and we want to block the alcohol. So we do that via the silyl ethers, the TBS, the tert-butyl dimethyl silyl group. It goes on there with the silyl chloride. It comes off with TBAF, the ammonium fluoride. And we'll do some multi-synthetic applications. Of course, once we learn a few reactions, then we'll go on. But we'll stay up here. Speaking of multi-step reactions, I like to point out here some common drugs. Many of you have probably taken Singulair, which is one of these newer generation asthma allergy drugs. It's a pretty complex molecule here. Aromatic rings. It's got a quinoline here, a couple benzenes, a cyclopropane here, sulfur, and a stereocenter, an R group right there. Just glancing through the synthesis, I don't expect you to reproduce these kind of things. I'm just showing you these to highlight how the reactions are useful. Here's a reaction right here with a vinyl Grignard reagent adding to an aldehyde, quench with water, and you get the allyl alcohol, that vinyl group added right there to that. We got a palladium reaction. Don't worry about that. We have an asymmetric reduction of this ketone to the S alcohol right there. Oh, and we got some protecting groups. There's a TBS group going on, a couple spots. Oh, a different protecting group there. Taking off the TBS group with TBAF, the fluoride, unmasks the alcohol, and then a mesylate leaving group is made. That's similar to tosylate. Maybe your professor for 351 didn't show mesylates, but here's a secondary leaving group, and then a charged nucleophile. The base is strong enough to take the proton off of a sulfide, and then that sulfur anion, what does the backside attack? And look, inverts that stereocenter. That puts that whole piece on, Singulair there. Anyway, you've probably seen that. There's a couple other reactions here making the cyclopropane piece. Yeah, some more SN2. I don't see any reduction. No, there's a reduction LAH, lithium aluminum hydride. Oh yeah, reducing both esters down to the alcohols. So you can, after you go through chapter 20 and learn these reactions, look back through these syntheses and you'll kind of see some things there. I like to point this out also. Ceravent here is this bigger, greasier drug here for asthma. It's longer acting, 12 hours, whereas the original drug, albuterol, in the inhalers, if you've taken this for asthma before, this is short acting. It only lasts about a half hour. Well, no, almost 2 hours in the body. Why does this one last longer, 12 hours? Yeah, it's greasier here. It's not as water soluble. It doesn't go out in the urine as quickly. It's not as metabolized as fast. This will persist in the lipid bilayer membranes and have longer duration of activity. So you only need to take it every 12 hours. Anyway. Oh, one more. Here's Ceravent, another asthma drug. And you can see it's an amine here, alcohols all over the place, a couple benzenes. It's a salt. It has this naphthalene carboxylic acid salt form here. Actually, this proton can be donated to the nitrogen, form the ammonium salt. This is the actual drug. And how's it made? Oh, some SN2 chemistry there. Let's see, bromination, I haven't covered that yet. Nucleophilic chemistry with an amine right there. Hydrogenation, that just takes off the benzylamine group. Let's see, are there some other reactions there? Nope, okay. Just some, oh, I wanted to point out the LAH reaction right there. So LAH, you see, reduces the ester to the primary alcohol, and it also reduces this ketone, you see, to the secondary alcohol. So you can already see some reactions. But we'll get to this later. This is the Cori asymmetric catalyst for the Diels-Alder, and we'll see this for an asymmetric reduction coming up later. So let's go to the board here and revisit the general mechanisms that we're covering here for all of the reactivity here in chapter 20. So, in fact, this summarizes everything in 21 also. So we have some sort of carbonyl compound, okay? If Z here, as I'm drawing it, is a hydrogen, that's an aldehyde. If it's a carbon, that's a ketone overall. But we can have derivatives of carboxylic acid if that's what, oxygen or nitrogen or chloride, okay? So it's a general thing. And why do I point this out? Well, this is a pi bond. So looking at the structure, sp2 hybridized, right? We got the pi bond there. We're bringing in a nucleophile, though, with its pair of electrons. So how does this reactivity actually work? This pi bond has 2 electrons in it. It's a filled molecular orbital. What orbitals are we actually interacting with? Well, we're interacting with the highest occupied molecular orbital of the nucleophile. That's that pair of electrons that's available for bonding. It's seeking out a nucleophile. That's what NU means, right? Wants to find a positively charged nucleus to dump off that electron density. Well, it's right there, the carbonyl, right? Because these electrons are polarized toward oxygen, right? And that's the mechanism of how we're going to react that. But we're not attacking the pi bond here. What bond or orbital are we attacking? Right, the empty orbital, which is the pi star, which looks like this, right? It has out of phase bonding there. The pi bond has in phase bonding, okay? The pi star, though, is this out of phase, and that's the empty orbital. So that's actually what we're going into here when we talk about this reactivity. And yes, we push the electron density off onto oxygen there, and we make the new sigma bond here. And what's the hybridization? It's a tetrahedral intermediate, right? So we rehybridize to sp3. We've seen this rehybridization before, right? So this mechanism follows that. If you can keep that straight, that's most of the battle here. And now, what group do we have here? If this Z group here in the beginning substrate was an aldehyde or a ketone, that's the end of the road. We just protonate the oxygen anion here with water. It's a second operation. It's called the workup step. We dump in water, or we dump in, dilute acid, whatever, okay? Sometimes that's better to get that to protonate. And then we get the alcohol product. So Z here is either hydrogen coming from an aldehyde or a carbon, another carbon from a ketone, and it's just an alcohol product, okay? But if Z here is one of these derivatives, we say, of a carboxylic acid, it has a non-carbon or non-hydrogen group there for Z, and that's a potential leaving group. So from our tetrahedral intermediate, what can occur here, instead of just quenching, is the Z group can function as a leaving group, okay? And those leaving groups, if it departs, goes to a new acyl product, rehybridizing to sp2. And notice, if this is just coming from a simple hydride or a carbonyl, it's a new aldehyde or a ketone. So you can get another equivalent of the nucleophile to add here and then quench with water, and then what do you get? You get 2 on there. That can be the confusing part of this, okay? But if you keep this overall paradigm in mind here and what the reactivity is going to be, why can we break these bonds in the second step? Well, they're heterobonds. They're weaker than a carbon-hydrogen or a carbon-carbon bond, okay? And that's not a good leaving group if this is hydride or carbon coming off, right? But these are electronegative, and they can potentially come off and give us a ketone or aldehyde product, which can do another operation. Anyway, so keep that straight, and you should be fine. There's another thing to keep straight here, and it's oxidation and reduction. And I like to talk about oxidation and reduction kind of together here with a hierarchy of functional groups, okay? So follow me here. Oxidation means what? Adding oxygen and or removing hydrogen, okay? That's what oxidation means in OChem. It's a little bit different in general chemistry. We talked about the charged state of a metal, for example. The reduced metal is the neutral form, the shiny stuff with the full complement of electrons to make it neutral overall. But if you pull the electrons out of a metal or oxidize it, you go to cationic forms of the metal, loss of electrons. But here we're looking at the functional groups, okay? You can look at the electrons and see what's being added there, okay? If we're putting on a heteroatom that's electronegative, we're pulling electrons out of that carbon. That's another way to look at it. Reduction is just the opposite. It means removal of oxygen and or adding hydrogen, okay? Let's look at a hierarchy of functional groups and see what this means. So how about methane, okay? Well, that has 4 hydrogens on carbon. So that's the fully reduced form of carbon, okay? What would be the next oxidized up one? Well, that would be methanol. Here we're adding an oxygen between one of the carbon and hydrogen bonds, okay? It's been oxidized. Can we oxidize that further? Yeah, we can create formaldehyde. Formaldehyde there, we're what? Losing 2 hydrogens. So you could say here, that's plus an oxygen. Here, this is what? Minus 2 hydrogens. It's the same thing. We're more oxidized as we go to the right here. Is there another one here? Yep. How about formic acid? Let's add another oxygen in there. Okay. More oxidized. Can we get more oxidized than formic acid? We've already got 3 bonds to oxygen. Can we make a 4th here? Yeah. So what about CO2? That's the end of the road for carbon. That's the most fully oxidized form of carbon. So everything this way is oxidation. And we can look at the reverse of this too, reduction. If we take a carboxylic acid and go back to an aldehyde, that's a reduction event. If we take a carboxylic acid and reduce it all the way to the alcohol, that's a reduction as well. Those are the reactions we're going to look at first. We're going to look at this one first, aldehydes, ketones, with sodium borohydride, lithium aluminum hydride, going down to the alcohol, okay? So we're going to look at that. We've seen oxidations before in chapter 12. We'll review some of those alcohols to aldehydes and ketones, or oxidize all the way, primary alcohols to carboxylic acids. But keeping that straight, you're okay there. So yeah, this is the fully reduced form. You can look at the electronegativities here of hydrogen, which is 2.2. Carbon is 2.5. So the more electronegative group here is actually the carbon, And if you push all the electrons onto the more electronegative group, that's what? Carbon in a formal -4 oxidation state. Now, we don't think of it that way. And then we've got, what, the 4 protons on carbon? No, these are covalent nonpolar bonds. But just looking at the electronegativity, you see this is the most reduced form of carbon, is the hydrocarbon. And same thing over here for this, right? Here, carbon would be in the +4 oxidation state. And then we have, what, 2 oxide anions, which are doubly negatively charged, but that's not what they are. They're sharing the electrons, but that's how it's react. In fact, we're going to use CO2 in reactions with nucleophiles, and yeah, you can push those electrons in with a strong nucleophile and get reactivity. Okay, and same thing here with the other carbonyls. But keep in mind this oxidation reduction pathway, they always go together. We'll show you how the reagent ends up oxidized. If the substrate's undergoing a reduction. If the substrate's undergoing an oxidation, then the reagent or some system must be being reduced, okay? There's a conservation of mass there and electrons and everything. But keeping redox straight can help you out. All right, let's look at the reactions here. We've got reductions of carbonyls. So the hydride reagents. I like to relate this to what we've already covered. Let's take an alkene with hydrogen and palladium. What do you get here? Hydrogenation, right? We're doing a reduction. We're adding hydrogen here. Okay, alkene to an alkane. The pi bond went away, rehybridized to sp3 hybridization. Well, it's really the similar thing here. If we have a carbonyl, which is again a pi bond, can we hydrogenate that with palladium or platinum? And the answer is yes. We pointed out in 351, it's a slower reaction, but if you have higher pressures of hydrogen and let this go longer or heat this up, you can get a reduction to what? The alcohol, okay? So yeah, why are we giving you a new reaction with hydride reducing agents? Well, they're a little bit different now. So sodium borohydride is the first one we're going to use, and it has a sodium cation. So what's the BH4? Well, it's boron with 4 hydrogens. And if there's 4 hydrogens here, boron has 3 valence electrons. So with 4 bonds now, what's the charge on boron? Yeah, it's borate. And you can see a hydride can come off, right? You can think of this as going to borane, which is neutral, plus H with a pair of electrons. There's your hydride. And that's what we mean when we say hydride. We're not saying proton or hydronium cation. We're saying hydride, hydrogen with a pair of electrons negatively charged. You can imagine that as the nucleophile. The true nucleophile is this. We'll get into the mechanism and you'll see how that adds. The other one is lithium aluminum hydride. Similar thing here, the lithium cation and then aluminum with 4 bonds. Aluminum also 3 valence electrons. It's the next row down. It's a bigger atom than boron. They're in the same family. Negative charge here. Now, lithium aluminum hydride is very, very reactive. Okay, sodium borohydride's of moderate reactivity. And we'll see that lithium aluminum hydride can react other things like carboxylic acids and esters and even amides that sodium borohydride cannot. So let's clear this up right now. Why is lithium aluminum hydride more reactive than sodium borohydride? Now, these are inorganic complexes, but can we apply some principles we know about chemistry to get to that point? Yeah, first of all, it's a bigger atom. Okay, it's more polarizable. And if it's a bigger atom here, these are longer bonds, these metal hydride bonds here. And because of their length, and this being a bigger atom, these are more available to transfer. So this is more reactive, okay? It'll be a better source of hydride than this, which is a smaller atom, shorter bonds, more stable, less reactive, okay? The book doesn't really point that out, and students always have questions, but I like to point that out. So this is gonna work just with aldehydes and ketones. This is gonna work with aldehydes, ketones, and a bunch of other derivatives, okay? That we're going to see there. So this is the more universal reducing agent. This is the less reactive one. Well, why do we have the two? This is a cheaper one, and it's more stable. It's safer to use. This one will catch on fire on the balance if you have a humid day and let it sit around. This one's actually pyrophoric. So I like to give you, the bottom line of why. If we have a functional group we need to reduce that won't be reduced as sodium borohydride, we'll use the more aggressive reducing agent. All right, let's look at a bunch of examples first here. And we'll get to the mechanism too. So we can take benzaldehyde and we can reduce it with sodium borohydride, BH4, and what do we get? We have to quench with acid, and we'll get the benzyl alcohol. Okay, so aldehyde to primary alcohol. What if we have a ketone? This sodium borohydride, same thing. Secondary alcohol now. Okay, LAH can work for either one of those, no problem. So anytime you have this, functional group, whatever, key on the functional group, the rest of the carbon framework just goes along for the ride. And with LAH or sodium borohydride, what do we get here? Primary alcohol from an aldehyde. Ketone, though, we get that, right? Ketones can be cyclic. We can take that with sodium borohydride or lithium and aluminum hydride, quench carefully with acid or water at the end. We'll see in the mechanism why that is. And what do we get? We get the alcohol. Now, part of it is you can look at this and say, okay, we didn't even draw this. That's the reagent, right? That delivered the hydride on carbon there. This hydrogen actually on the oxygen came from water, okay? So you can keep that straight in your mechanism. And looking at the carbonyl reactivity, you can already see how that's going to work. Now, there are some issues here. What if we have a stereochemistry issue? So here's 4-methyl cyclohexanone. Let's do the reduction here. What are we going to get? Well, we're going to get the secondary alcohol. Which one? So even though you can keep track of this relatively simple reaction, we've got some complexity here. Is this hydride going to come in from the bottom, away from the methyl, or on the top? Now, that's a rule we don't expect you to know, but look at this. You can generate 2 different products. If it came on the top, you get that, and if it came on the bottom, you get the cis one, okay? So yeah, appreciate some of the complexity here. Here's trans, here's cis. Okay, we're letting you off the hook there, but be aware of these stereochemical issues. This is not a chiral molecule. You've got the symmetry down the middle here. But when you add the hydride and convert that into alcohol, look, you've got the relative stereochemistry here. And both of these, by the way, are achiral. What are these relative to each other? Very good, they're diastereomers, okay? But they're both achiral, okay? But they are stereoisomers, cis-trans isomers on the ring there. Achiral, both of them. Anyway, things to worry about. How about this one? Now this one's a little bit different. I just moved the methyl over to the 2 position now. Now what? This is actually chiral, okay? What's the stereocenter here? Let's see if I can do that real quick. I think that is R, okay? This is not a stereocenter, right? This is a stereocenter. And if we do the cis and trans deal here, what do we get? We can get the cis again, plus the trans. I won't draw it, but both of those are chiral now. There's no mere plane in there. So even though it's a simple reaction, you've got some complex stereochemistry. We'll show the asymmetric catalyst here in a minute and how we deal with that. Now, LAH is more reactive. It works for all of these here also, like sodium borohydride. So let's see here, LAH. And LAH means lithium aluminum hydride. You can just use the acronym on a quiz or the test. Sometimes that's all we show. Sodium borohydride, we don't use the acronym for that. LAH, more universal, more useful, we do use the acronym. And we have to have the water or the acid quench here. And what do we get? The same thing, primary alcohol. Okay, ketones also. Here's a ketone. with LAH, and what do you get here? You get the corresponding alcohol. All right, let's look at the mechanism of borohydride. So here you go. Let's keep it simple. Acetaldehyde, sodium borohydride, and we're going to go to ethanol. Okay. And we got water. Let's have the whole thing in there. First of all, notice the charges on the reagent. It is an ionic inorganic salt. What can we do there? Well, let's have the lone pair interact with the sodium and form a Lewis acid complex. Now, if it does that, now your charge is on oxygen. That makes that oxygen now more susceptible to nucleophilic attack. Where's the nucleophile? It's the borate. Okay. Negatively charged, 4 bonds to hydrogen. How does this work now? Well, you see, it's more susceptible to that attack, right? So we can get the hydride on there, the sodium. The other hydrogen was already there, but let me circle that one that just went on there with its pair of electrons, right? To go to the sodium alkoxide, we say. We could draw this anionic too. We could have sodium plus if we just push these electrons here and O minus, okay? In fact, I'll do that. What else do we have at this point though? We still have BH3, right? As this one hydride came off, we still have the 3 hydrogens there. What else can occur here? Now, this is a Lewis acid. It has an empty orbital right here. Let's put that other one on there. Now we have BH3, borate again, and sodium cation, okay? Now, what can occur at this point? Well, we've got more substrate, okay? We can have more of that. And look, more hydride can attack here. In fact, it can do it 2 more times from that. So we don't actually need a full equivalent of sodium borohydride. We can actually just use 1/4 of an equivalent, and all of these hydrides can transfer over via this sequential step here. You create a new borate each time you do a hydride addition. So what you'll end up with at the end is this, actually. Boron with 4 ethoxy groups on there, okay, at the very end. Now, water at this point comes in, and I'm not going to go through all this, but water eventually transfers the hydride, and then OH gets transferred to boron, and you wind up with the alcohol product, okay, and you wind up with boric acid, or trihydroxyborane. Now that sounds like it's a hydroxy group. It's not. This is boric acid. This is the stuff you use to clean your contact lenses every night. Okay, it's a mild acid. It's not a hydroxide. That's some inorganic chemistry. You don't need to worry about that. And you don't need to worry about this last step here. All you need to worry about is this first part here. In fact, from here to get to the product, look, all you need is water grabbing the proton here off the alkoxy group. And that's what? Just a strong base now, like we've talked about before, and you're protonating it to give the neutral product, okay? But be aware, you only need 1/4 of an equivalent there, okay? The key of the whole thing is nucleophile adding to a carbonyl, okay? And that fits into everything we've covered before. Let me show you some important flexibility of these reagents now. So here's a molecule with 2 functional groups, an alkene and a ketone. What if we want to go to this? What if we want to go to the ketone and just reduce the alkene? What reagent would we use? Yeah, from 351, hydrogen and palladium. Now we wouldn't use excess or pressure or a long time because we could reduce that, right? In fact, yeah, hydrogen, high pressure, and time. You got to have the catalyst. In fact, a platinum catalyst works better, or rhodium. Then you can get the fully reduced thing, okay? You can get the alcohol alkane, okay? What if we just want to reduce the ketone or an aldehyde in the presence of an alkene? Yeah, then we use sodium borohydride, okay? Show the quenching step, the water or dilute acid. And what do we get? Yeah, the alcohol alkene. So there's all three possibilities, right? So we can do the full reduction, partial reduction of one functional group, the alkene, or partial reduction of it, just reducing the carbonyl, okay? So we've increased the flexibility of these reagents here. All right, let's look at LAH with these agents here. So we've got carboxylic acid, and we've got esters, and LAH, and water, and look at this. You go to the alcohol, okay? What about this one? Oh, you reduce the carbonyl, and this looks kind of funny, but you get two alcohols? Yeah, you're going to get this alcohol when it comes off the tetrahedral intermediate, and then you're going to reduce here, okay? And notice when you say reduce with LAH, there's two hydrides that need to go on there from LAH. There they are, okay, on that substrate. These two hydrogens here were on the original ester part right there. But get this, so sodium borohydride with these guys, no reaction, okay? It does not reduce acids and esters. Why? Because it's smaller, shorter bonds, okay? But LAH can do these type of reactions. Here's another one to show you. How about if we have a aromatic ester like this, and we do LAH, and quench. Look, we're going to form benzyl alcohol. Now the two alcohols are different. And we're going to form isopropyl alcohol. We're going to form these two products, okay? But again, the hydrides went on the carbonyl side. So we need to look at the mechanism here. Let's see. One other thing here on the stereochemistry, and then we'll show a little bit about asymmetric catalysts in this variation. So you can take this reagent, substrate rather, sodium borohydride, do the reduction, quench with water, and look, we've got a ketone that's not symmetric on each side. We can get this enantiomer plus this enantiomer. Okay, so this is what, the S, I think? And is that the R? Yeah. And so this is racemic. Now you can just draw it as a straight line and say DL or plus minus, right? That's what we've done before. But I want to show you, how did this arise? So here would be the hydride adding on the top face, okay? That would be the S pathway. Or on the bottom there, that would be the R pathway, giving this guy, okay? So the stereochemical result can be important here. Let's go to the overhead and see an asymmetric catalyst for this. If you can move the camera up there to the overhead. We've seen this asymmetric catalyst right here for this Diels-Alder reaction. There's cyclohexene with the ester going along for the ride. And you need this trifluoroethyl ester to get there. There's your dienophile. Here's your diene. And there's just one stereocenter. All the other stereocenters here in Tamiflu are directed by this stereocenter being formed with high enantioselectivity. It's kind of why the drug's expensive. It takes 12 steps or so to make Tamiflu, but it works very well. Okay, and it's a more recent drug developed using rational drug design. I'll say more about that later. It actually mimics a sugar. So when we get to the sugar chapter, we'll say a little bit more about this rational drug design. But I like to point out these reagents. Now the same catalyst here, it's called the Corey-Bakshi-Shibata catalyst. Here's the S form of the catalyst. You don't need a full equivalent. You can go as low as 1 mole% of this, but it's the S form. There's the stereocenter right there. Okay, it comes from proline, the amino acid proline, which has that 5-membered ring in it. We'll say more about that later when we get to amino acids, of course. This is an bora-oxazoline. It's got these 3 heteroatoms in a ring here. And it has borane, which is the actual reducing agent. But here you take a ketone that's unsymmetrical, a phenyl and a methyl, and you get the R only alcohol product in high enantiomeric excess. That's what EE stands for. So 98% Over 98. Actually, that means it's 99% R and only 1% S. And you take the major minus the minor, and you get the EE value, which is 98. So it's actually a little better than that up here. You can oftentimes recrystallize these alcohols, and they'll be essentially pure, 100% the enantiomer you want. So how does this work? The catalyst is chiral. So its stereocenter can be transferred to the product. And this is the basis of reactions in biology also. Different enzymes will create new stereocenters in different metabolites. You see all the molecules in nature, sugars, amino acids, cofactors, and a lot of other molecules in nature are chiral. Where did those stereocenters come from? Well, chiral catalysts. We'll see later on that they're actually enzymes that are chiral. This is a chiral reagent. This is not an enzyme, but the same principles hold here. The chirality of the catalyst is transferred to the substrate to give a chiral enantiopure product. Here's the mechanism. I don't expect you to know this, just the principles of it, okay? So the carbonyl lone pair coordinates the boron. That's Lewis acidic. There it is coordinating, okay? The nitrogen of the catalyst also coordinates, but the reducing agent, the borane, that's where the empty orbital is there. There's a pair of electrons on the nitrogen there. There's the complex, okay? And the ketone is positioned such that the methyl group, which is smaller, is next to this methyl group, and the larger phenyl group's down. And so from the front face here, hydride is transferred. You push electrons. You got to do some more steps here. You get the borate here. The boron byproduct here grabs this oxygen off the borate of the catalyst, and it sits like that until you quench it. And then you just protonate there to get the alcohol, okay? But you see, it's organizing the transition state, the hydride delivery, such that you just get the one R enantiomeric form. You do get some of the S, though, in this case, and that's if it's flipped around the other way or delivered from the other side, or it's not complexed in the lowest energy conformer like I've shown here. Okay. Normally, we cool these reactions down as much as we can. And here's the bottom line, this energy diagram. We're starting right in the middle, and we're going to the right to form the R product, and we're going to the left, you see, to form the S enantiomer. They're the same energy. Notice they're the same ground state energy. There's no difference in energy between the two enantiomers. But the pathway leading there is different, right? So here is the S catalyst doing the formation of the R stereocenter. And this diastereomeric transition state is lower in energy than the SS pathway. Okay, the catalyst is still S here, but if it's leading the S product, you see that's going to be a diastereomeric transition state. Now, I'm not drawing that SS transition state. I kind of described how it's higher in energy there. But you see that's the relationship. SS to SR, that's diastereomeric. Even though the product's S to R, that's enantiomeric. They have to be the same energy. But the transition states are different. It's actually a kinetic effect then. Okay, the transition state leading to the major enantiomer is faster. Why? Because it's lower in energy than the higher one right there. So anyway, hopefully that gives you a little bit of an idea there. Let's look at Mother Nature's reducing agent. And here we've got it. We've got NADH. Come back over here to the board. I'm not going to draw the whole reagent of NADH. It stands for nicotinamide adenine dinucleotide reduced form, NADH. Okay, and if I were just showing you the top part of this cofactor, the cofactor is quite large. It's got an adenosine nucleoside, and it's also got a big protein that binds to it. Okay, so this is just the cofactor part. But there's two hydrogens here, and here's a typical substrate that's going to get reduced. Let's look at pyruvic acid. We'll see pyruvic acid later on in glycolysis. It's the end of glycolysis, the conversion of glucose into pyruvate, if you've learned some metabolism before. Pyruvate gets reduced to lactate. And it does so, you just get the one isomeric product here, R or S. Is that S? Yep, S. Okay. And it is pyruvate. I'm going to ionize that because we're in aqueous solution at pH 7. So that will be ionized. It will be pyruvate. Okay, the carboxylate. Why? Okay, remember chapter 19, the acidity of carboxylic acid. pH 7 is ionized right there. But you see, this gets reduced to the alcohol. And that's lactate, lactic acid or lactate. What happens to the NADH? It becomes NAD plus. And I like to point this out. You've seen this designation before, probably, NAD plus. That's a new cofactor. That's used in oxidation reactions. There are ways to convert it back, of course, to NADH. But how does this work? Let's see. Well, there's a big enzyme, a reductase, that coordinates the whole thing. This is just the cofactor. Okay, and here's the substrate. Okay, so mechanistically, can we push electrons and see? This isn't sodium borohydride or LAH now, but that is a ketone to an alcohol, right? How does it work? Let's bring a pair of electrons here, over here, and bring the electrons there and push up there. Okay, so what do we get? We get the O minus there, carboxylate, and then the enzyme actually has a protonated basic side chain, which functions as a proton source. In fact, those are concerted. It's the hydride delivers there. We do that. So this pair of electrons off this amine right here, and because we have two hydrogens right here, one of them comes off as a hydride, and it's that one right there that ends up on our substrate. So it's similar to sodium borohydride that way, or lithium aluminum hydride. Why is it the S form only? Okay, 100% S from this reductase enzyme. Right, this enzyme is chiral. Okay, it's an antiopure. Even though the cofactor looks flat, there's no stereocenter there. By the way, it's called nicotinamide for a reason. It does have a relation to nicotine. You've probably heard from cigarettes. It's a pyridine amide. Okay, it's called a nicotinamide. But that's the key cofactor, delivering a hydride to a ketone to make this. Now, there are other substrates that get reduced in biology. The NADH is now positively charged right there on that nitrogen, that formal charge. We needed to add that in. It is reversible under different conditions where we could have a base take this off, flow the electrons back in, and reduce the NAD plus back to NADH. And what? Oxidize this back. Okay, so forwards and backwards, you can kind of see how that reaction is going to work. All right, let's summarize our key reactions here, what we've covered so far. I'd like to give a summary to help you with reactivity, keeping these things straight. So how about this? Aldehyde, sodium borohydride, or LAH. What do we go to here? We go to the primary alcohol, okay, from the aldehyde. What about a ketone? And any type of ketone, either of those reagents, right? Secondary alcohol, aldehydes and ketones. What about carboxylic acids? Now here we have to use LAH, okay? And LAH, we'll go through the mechanism of this too, goes to the primary alcohol, not sodium borohydride, okay? That does not work with this. Or esters, you can take an ester here, LAH, and what do we get here? We can get the alcohol there that corresponds to the carbonyl part, plus the alcohol off the alkoxy part there, okay? Well, what if we want to stop here, take an ester, and stop, instead of at the, going all the way to the aldehyde, or the primary alcohol there, what if we want to stop at the aldehyde, okay? What are we going to do there? Well, yeah, we need to use an attenuated lithium aluminum hydride reagent, and that will be this reagent called dibol, okay? Diisobutyl aluminum hydride, and it only has one hydride on it. LAH and sodium borohydride have 4 hydrides, right? But these less reactive ones that let us stop after just adding 1 here to the aldehyde is attenuated in reactivity there. So let's see what some of those are and go through some of these mechanisms. There's a universal mechanism for this, so don't worry about it too much, but we'll see how the reactivity goes. Dibol is this. Diisobutyl aluminum hydride. Here's 2 isobutyls on there. And thank goodness for acronyms. You don't want to have to draw that out every time. You see the 2 isobutyls here on aluminum, and then the hydride, okay? Sometimes we draw it as dibol H. Either way, you need to recognize there's just 1 hydride on there. And that will be esters to aldehydes, okay? And then we have another attenuating reagent, and that's tri-T-butoxy aluminum hydride lithium salt. Okay, and that's a mouthful too. So 3 tributoxy groups. This is tert-butyl, oxy. 3 of those are on aluminum with 1 hydrogen. So this is negatively charged overall, and then lithium's plus charge. You don't have to draw those in. But tri-T-butoxy aluminum hydride will take acid chlorides also to aldehydes. Okay, so we have those 2 functional groups that are useful. We've seen acid chlorides before for Friedel-Crafts acylation. We'll see esters a lot, and those are very common in biology, so we need to learn about those. But you see, if we just add 1 hydride, and both of these just have the 1 hydride, we stop at the aldehyde stage. Okay, so let's see them in action here. We've got this acid chloride. If we react with LAH, quench with water, we'll get the alcohol. Okay. If we react with tri-T-butoxy aluminum hydride, we'll go to the aldehyde. Okay. The ester, corresponding ester, oh, let's make it a different ester. How about this one with a benzene in it, ethyl ester? If we react with LAH and quench with water, I'm not putting that on there, but yeah, you always should. You go to that. What happened to the ethanol? It's there. A lot of times we don't worry about the smaller part of the ester coming off. A lot of times we're only worried about the carbonyl part. But, you know, you should recognize both are there. This is so water soluble. A lot of times when we do the workup and aqueous extraction with an organic solvent, we'll just get the heavier one. And that's often the one we want to look at. But if we want to stop at the aldehyde from this ester, what we use dibol. So yeah, you can just use the acronyms, and that's fine. And what do we get? We get the aldehyde product. We also get the ethanol coming off there, but the key is the reactivity. Okay, yeah, you should be okay on the reactivity. Let's do the mechanism briefly, and then we'll wrap up. I think we got a few more minutes. Okay, yeah, we got a few more minutes. Let's get into the mechanism. And yeah, second hour, we'll be doing the Grignard reagents. So yeah, I told you there's a lot of reaction in this chapter, but you're doing okay. Okay, yeah. Let's see, so what's the mechanism here? All of these are really the same. Just got this Z group here, right? And so what do we have? With LAH, we've got, you know, aluminum, 3 hydrides that aren't reacting there, and 1 that is. And, you know, we're reacting here, push the electrons up, and we get O minus here, and the Z. Whatever the Z is, we'll see that can even be an amide. It can be a chloride or an O for an ester, right? Or an OH for carboxylic acid. And so this can come back down and comes off, you see. And what? The intermediate is actually an aldehyde at that point, right? And what? We've still got 3 of these on here. So at this point, you know, we've got the aluminum H3, and we can react that, right? And what do we get? Aluminum H3, Z, okay. And, you know, this hydride can go onto that. How do we get the group to come off? Well, we have this come back off like that. And we got the aldehyde. And now we got the aldehyde. That can coordinate the aluminum again, right? And then we have the ability to add another hydride here. And that gives us what? It gives us 2 hydrogens on there now. And O and aluminum Now it just has the 2 on there. Okay, so you can kind of keep track of the aluminum. We start out with 4, go down to 3, transfer 1, recoordinate the carbonyl, the aldehyde, and then add another time. So both of these came from the aluminum hydride. And then at the end, when we put in water, that's the second operation. This can grab the proton there, and we get the product. So that's kind of the general thing, going from any of these derivatives down to the primary alcohol. Now, let's compare that with this. If we've got dibol now, this is going to be a little bit different. And dibol, remember, is specific for esters. So let's draw an ester here. And dibol is the aluminum diisobutyl hydride. Okay? Now it's still Lewis acidic, so I can still coordinate here and form the Lewis acid complex. And I'll just say, 2 isobutyl groups on there. I won't keep drawing it. But, keep track of your charges here if you'd like. And what do? We transfer here, okay? And we get this. OR, H, there's our O, R2, okay? And notice here, at this point, we can what? We can lose the aluminum off there, but actually this will sit like this until we quench with water, okay? We don't have any more hydrides on aluminum at that point. We've just added the 1 here. But when we do quench with water, what can occur here is we can coordinate the water lone pair into the empty orbital there. This will actually come off, and this will come off and get protonated there. And at that point, we generate the aldehyde, and that's all we can generate because we only had the 1 equivalent of hydride to begin with there. This gets protonated. The small alkoxy group coming off is indeed an alcohol when it comes off. And the aluminum ends up as aluminum hydroxide with the 2 isobutyl groups on there. But the key thing to point out here is that the dibol and the tri-TB-toxy aluminum hydride reagents, which are specific for acid chlorides, not esters. Esters are with dibol. So you just have the 1 hydrogen here. Here it is right here. It ends up on the tetrahedral intermediate. When the tetrahedral intermediate then breaks down upon quenching with water, the aluminum gets that extra oxygen from water, and the proton ends up on that. Okay, so I think that's all you need to know on the mechanism there. And I think we'll end it right here. So very good. Stay tuned for the second hour.